Welcome viewers to the second segment of the third lecture for the online series of lectures for the course of Algebraic Topology 1. Towards the end of previous segment, we discussed this example, a rather trivial example of covering map and covering space of a given topological space X. The total the topological space E in this example was an n-fold product of this given topological space X that you can see here in this diagram. Okay, but it was a very trivial example. So in this segment we are going to study first an example which is a non-trivial example of covering space of a unit circle on the two-dimensional plane. Okay, so let me erase everything here. So in this segment we are going to study the example of the following covering map. Define a map P from the real line to the unit circle by P of x is equal to cosine of 2 pi x sine 2 pi x. Okay. Alright, so let us draw a circle first. So we have a circle here, a perfect circle, with the center being, and the x-axis given by this line and the y-axis given by this line. Okay, this is our x-axis, this is our y-axis. Okay, and the point located here is the point 0 or minus 1, and the point up here is 0 plus 1. Okay, and in this diagram we have an arc here, which is this bold part of the circle, this arc between these 2 points 0, 1 and 0 minus 1. We denote this arc with U1. Okay, alright, and the arc intersects the x-axis at the point 1, 0. Alright, okay, good. So now we call this theorem 1 in this example. One needs to prove that P is a covering map. Okay, so the proof goes as follows. So like I said before, that we draw a unit circle centered at the point 0, 0. Okay, in the xy plane, draw S1 centered at 0, 0 in the xy plane. Okay. Locate the point 1, 0 on the x-axis situated situated 1 unit away from the origin 0, 0. Okay. Now observe that this point 1, 0 on the unit circle corresponds to x equal to 0 for this map. Okay. This 1, 0 point on S1 corresponds to 0 in R via the map P. Okay. There are other points in R that also correspond to 1, 0. Okay. What are those points? Say x is equal to 2. Okay. That corresponds to 1, 0 as well, right? Because for x equal to 2, I have cosine 4 pi, which is again 1, and for sine 4 pi, I have 0. So for x equal to 2, meaning that p of 2 is again 1, 0. Similarly, you will be able to see that p comma minus 1 is also 1, 0. In fact, p of z is equal to 1, 0. Right. So p of z is this singleton containing only the point 1, 0. Right? So this is what we are going to write here. In fact, all the integer points in R correspond to 1, 0 on the unit circle via the map P. In other words, this can also be rewritten in the following way. Inverse image of the point 1, 0 on the circle is going to be the set of integers, which is of course a proper subset of the set of real numbers. Okay, so using this figure, the figure of the unit circle here, and the formula for P, one immediately sees that the inverse image of this point 0, 1 or the north pole here is going to be n plus 1 over 4, where n belongs to the set of integers, right? Immediately, because if you plug in um, um, n plus 4 here. Okay, if you plug in n plus 4 here, n plus 1 quarter here, you plug in n plus 1 quarter here, what you get is the following. It's going to be cosine 2 pi n plus pi over 2, and the y coordinate is going to be sine 2 pi n plus pi over 2. Okay, and twice pi n plus pi over 2 is just 0, and sine 2 pi n plus pi over 2 is going to be 1. Okay, so the inverse image of 0 comma 1 is the set of all points of the form n plus 1 over 4, where n belongs to the set of integers. Okay, similarly, the inverse image of 0 comma minus 1, the south pole of the circle, the south pole of the unit circle, is going to be n minus 1 quarter, where n belongs to the set of integers. Okay, just plug in n minus 1 quarter here and n minus 1 quarter here to see that we're going to get 0, negative 1. Okay, the x coordinate is going to be 0 and the y coordinate is going to be minus 1. Okay, so let me create some room here. I don't need these things anymore here. Okay, good. Okay, so the open arc denoted by this u1, okay, between 0 comma 1 and 0 comma minus 1, there is an open arc u1, has the free image P inverse u1 to be equal to the disjoint union of all the open sets from n minus 1 quarter to n plus 1 quarter. Okay, right? Well, you can draw a line, and putting all these intervals on the line, you'll see that they are all disjoint, meaning that if you take a pair of any two such intervals, then their intersection is going to be in the empty set. Okay, so this is the open arc between 0 minus 1, the south pole, and 0 1, the north pole. Okay, so now a few facts about this map P. Is P can easily be seen to be surjective. P can easily be seen to be surjective. Okay, so the way we see it is to cover to cover the entire unit circle uh, by open arcs. Okay, let us have a closer look at how we do that. So one arc is this arc U1, and we can also have other arcs. Say we have seen that for this arc the pre-image is the disjoint union of open intervals, right? N minus 1 quarter to n plus 1 quarter, right? And for similarly, you should be able to see that when you have this open arc, which we denote by U4, you can take the pre-image of U4 under the map P and have it to be the disjoint union of these intervals n plus 1/2 to n plus 1. Okay. And you can go on to see that the open arc U3 here, this guy, this arc U3 has a pre-image equal to disjoint union of the following open intervals n plus 1 quarter to n plus 3 quarter. Okay. Finally, when you have this open arc, the top open arc, okay, which we call U2, then the inverse image of it is the disjoint union of the following open intervals in R: n comma n plus 1/2. Okay. All right. Now, important thing to note is that these 4 open sets cover S1. In other words, this is an open cover of S1. Okay, so if you pick up any point on the unit circle, that is going to be in at least one of these open arcs in S1. And we have seen that there is an inverse image. There is this, the inverse image of all these open arcs are given by these formulas. Okay, so if you pick up any point on the unit circle, that is certainly going to have an inverse image under P. That is why P is surjective. Okay. All right. The second fact is the following. Let me erase these things here. Note that P can be seen to be a map P from R to R cross R. Okay, because you think of S1 being embedded in R2, the two-dimensional plane. In other words, the XY plane. Okay, and it's given by P of x is equal to P1 of x, comma, P2 of x, where P1 is a map from R to R. The x-coordinate map is a map from R to itself, and so is P2, and they're given by P1 of x is equal to cosine 2 pi x, the x-coordinate function, and the y-coordinate function is given by P2 of x is equal to sine 2 pi x. Since both P1 and P2 are continuous maps, P is also continuous, okay, by Theorem 18.4. It's the page number 110 of the same book that we are following for Algebraic Topology course. Okay. It tells us that if the component functions that we are dealing with, uh, uh, if they are continuous maps, the map P is also a continuous map. Okay. So for the detail, go at page 110 of the book by Moncrief to see what this theorem is about. Okay. All right. Now we have seen that. Okay, let me raise things here. Now we have seen that. Well, we have discussed earlier that this family is an open cover of S1. Okay, and if one can show that each of the open subsets, these are open subsets in S1 in subspace topology. Open subsets, in subspace topology of S1 inherited from R2. Okay, if one can show that each of these open sets is evenly covered by P, then one ends up proving that P is a covering map of S1. Okay, so what we are saying is that we need to prove that each of these open sets are evenly covered by P. Okay, this is what we need to show, and this will prove that P is a covering map, because for the definition of covering map, one needs to show that for each point of the circle S1, we can find an open set that is evenly covered by P. That is something that we need to show to prove that P is a covering map. But since we are proving that all these four open sets are evenly covered, and since any point on the open set will have one of these four sets as its neighborhood, one ends up proving that that point uh, is contained in a neighborhood that is evenly covered. Okay, all right. So let's try to prove that one of these four sets is evenly covered, and to prove that the other three open sets are also evenly covered uh, can be done this same way. Okay, so we will leave uh, that to the readers. Okay, so here we'll only show that U1 is evenly covered by B. Okay. All right, this is what we are going to show. Okay, earlier we saw that the inverse image of U1 under P is the disjoint union of these sets, open set from n minus 1 quarter to n plus 1 quarter. Okay, so let me draw a picture for it. Okay, let me erase everything and try to draw a picture of it. So here I have this circle, and this is the x-axis, and this is the y-axis. Okay, and this point is 1 comma 0, and this is the open arc that we are considering, denoted by U1. Okay, let us make it bold as before. Okay, now here is the line this is 0, and let us mark -1 here, +1, then we have +2 here, then we have -2 here. Okay, so this is 1 quarter, this is okay, a little smaller, this is 1 quarter, this is 1/2, this is 3 quarter, and this is 1. Again, this is 1 quarter, this is 1/2, this is 3 quarter. Okay, so similarly, this is -1 quarter, this is -1/2, -3 quarter, this is -1, this is 1 quarter, this is 1/2, then 3 quarter. Okay, okay, so well, we know that the inverse image of U1 is the disjoint union of these open intervals n minus 1 quarter to n plus 1 quarter. So we call these open sets V sub n. So V sub 0 is the open set -1 quarter to +1 quarter, which is this set, right? Okay, this is -1 quarter to +1 quarter. Now, for when we plug in 1 here for n, we have um, 1/2 to 5/4. I think when also this is So when we plug in 1, we have 3/4 to 5/4, which is slightly here. Okay, somewhere here, 3/4 to 5/4. This is going to be V1. This is V0. Similarly, plug in 2 here to see that you're going to have this thing here. From 2 minus 1/4 to 2 plus 1/4. This is going to be V2. Similarly, minus 1 plus 1/4 to minus, no, sorry, minus 1 minus 1/4 to minus 1 plus 1/4. That's V minus 1. And for V minus 2, it's going to be minus 2 minus 1/4 to minus 2 plus 1/4. That's going to be V minus 2. Okay, so this way you see that these open sets are disjoint open sets. Okay, and the union of these disjoint open sets is going to be the inverse image of U1. Okay, the caption of the figure is Vn. It's simply Vn from n minus 1/4 to n plus 1/4. Okay, so it depicts few of the open sets of the family, okay, which are mutually disjoint from each other. Okay, so from the figure, it's immediate that the open sets Vn that we define to be n minus 1/4 to n plus 1/4 for n belonging to the set of integers are disjoint. Okay, one just needs to show that be restricted to V sub n from Bn to U1 is a homeomorphism for each n belonging to the set of integers. Okay, so the restriction of the map, the map that we defined by P of x is equal to cosine 2 pi x, sine 2 pi x. The restriction of this map to this open sets is a homeomorphism from Vn to the open set U1 of the unit circle is a homeomorphism. That's what we need to show. Okay, so the trick is to show first that the restriction of this map to the closure of Vn, which is the closed interval from n minus 1/4 to n plus 1/4, is from the closure of Vn to the closure of the open arc U1, which is the closed arc, is a homeomorphism. This is something that we need to show first. Homeomorphism, where this bar stands for closure. Okay, example is the following. The closure of Vn is going to be n minus 1/4 to n plus 1/4. Okay. Okay. So this is a closed interval. For a given n in the set of real numbers, and U1 bar is the closed arc arc in S1. Okay, so let's see how we can do that. Okay, so let me erase things here. All right, I want to first show that this map that we are dealing with now, be restricted to the closure of Vn from the closure of Vn to the closure of U1. This map is injective. That's something that I need to show first. Okay, let's assume that cosine 2 pi x1 comma sine 2 pi x1 is equal to cosine 2 pi x2 sine 2 pi x2. Okay, let us assume that. Okay, in other words, we are assuming that we okay, all right, be restricted to Vn bar x1 is equal to be restricted to Vn bar x2. This is what we are assuming, where we are assuming that this equality holds, where x1 x2 belongs to this closed interval n minus 1 quarter to n plus 1 quarter for some fixed n in the set of integers. Okay, so if this is the case, if x1 x2 they belong to this closed interval of R, then we immediately see that 2 pi xi belongs to 2 pi n minus pi over 2 to 2 pi n plus pi over 2 for I is equal to 1 2, meaning that 2 pi x1 belongs to this interval, this closed interval, also 2 pi x2 belongs to this closed interval. Okay, so the picture for this is the following. Well, we immediately see that. So on the x-axis we have 2 pi x, and on the y-axis I have sine 2 pi x. Okay, so I'm trying to draw the picture for sine 2 pi x. Okay, and suppose we are so we're just considering n equal to 0 case. So I have negative pi over 2 and positive pi over 2. So the caption of the figure is 2 pi x belonging to this closed interval 2 pi n minus pi over 2 to 2 pi n plus pi over 2. We are considering this 2 pi x belonging to this closed interval for the case n equal to 0, which means that 2 pi x belongs to the closed interval from negative pi over 2 to positive pi over 2. So 2 pi x belongs to this closed interval. Okay, and in this closed interval, okay, this is plus 1, this point, and this is minus 1, right? These are the two extremes, because it's a trigonometric function. Sine 2 pi x and sine 2 pi x goes from negative 1 to plus 1. Okay, these are the two maximum possible values. I mean that the smallest negative value that it can achieve is negative 1, and the highest positive value that it can achieve is positive 1, and it's a sinusoidal wave, something like this. Okay, all right. So if this pair is equal to this pair, then the coordinates should be the same, meaning that cosine 2 pi x1 should be the same as sine 2 pi x1, and we also need sine 2 pi x1 to be equal to sine 2 pi x2. So to have these pairs to be the same, we want cosine 2 pi x1 to be the same as cosine 2 pi x2, and sine 2 pi x1 to be the same as sine 2 pi x2. Okay, so let me erase. So what do we want? We want cosine 2 pi x1 to be equal to cosine 2 pi x2, and we want sine 2 pi x1 to be equal to sine 2 pi x2. Now, since the trig function sine is a monotonically increasing function for 2 pi x psi, let me write it. Since the trig function sine is monotonically increasing continuous function for 2 pi xi in this interval, 2 pi n minus pi over 2 to 2 pi n plus pi over 2 for I 1, 2, with n belonging to the set of integers. Okay, so this is a picture showing that it's monotonically increasing. Okay, strictly increasing continuous function. Okay, so since it's monotonically increasing in this interval, to have sine 2 pi x1 to be equal to sine 2 pi x2, one must have x1 to be equal to x2. There is no other way these two functions can be, uh, uh, this equality can be held. Okay, there is no other way. That's the only possibility. x1 is equal to x2, since it's a monotonically increasing function, increasing continuous function. Okay, so we just have verified that P restricted to the closure of Vn at x1 is equal to P restricted to the closure of Vn at x2 implies x1 is equal to x2. Okay, and which means that this restriction function to the closure of Vn, from the closure of Vn to the closure of u1, is indeed injective. Okay. Okay. Good. Now we need to prove that it's surjective. In other words, we are going to prove that it's bijective, right? For the surjectivity part, observe that P restricted to the closure of Vn, from the closure of Vn to the closed arc U1 bar of S1. For this map, the endpoints of this closed interval, which is what? N minus 1/4 and n plus 1/4. These are the boundaries. Okay, n minus 1/4 and n plus 1/4 are the boundaries. These 2 points constitute the boundary of this closed interval. Okay, and these 2 endpoints are going to map to the the north pole and the south pole of the of the arc U1. Okay, because you see that what was the functional expression P of x is equal to cosine 2 pi x sine 2 pi x. Okay, so if you plug in n minus 1 quarter here, you get cosine 2 pi n minus pi over 2 sine 2 pi n minus pi over 2, which is well, cosine minus pi over 2 and sine minus pi over 2. Okay, which is cosine minus pi over 2 is going to be 0, and sine minus pi over t is negative 1. Okay, so that's one endpoint of the closed arc U1 bar. Okay, recall that how does it look? This was the circle, and this was the arc, open arc U1, right? So the endpoints here for the boundary points of the closure are one. This is the south pole, which is 0 comma minus 1, and p, similarly you can show that p of n plus 1 quarter is equal to 0 comma 1. Okay, you plug in n plus 1 quarter for x, okay, and you get 0 comma 1. Okay, that's the north pole, which is the other endpoint of this closed arc in S1. Okay, so it means that for this map, the endpoints of Vn bar are mapped to the endpoints of U1 bar. Okay, and this is a continuous map, and which means that by intermediate value theorem, by intermediate value theorem, for any C, any point on the open arc U1, there exists X in the open set Vn such that the map we are considering V restricted to Vn bar at X is going to be equal to C. In other words, V restricted to Vn bar is surjective. So what did we prove? So let me erase everything. So we have been able to prove that P restricted to the closure of Vn from Vn bar to U1 bar is a bijective continuous map, right? This is what we have proved. Okay, so it's a bijective continuous map. Now, the closure of Vn being the closed set from n minus 1 quarter to n plus 1 quarter is a compact subset of R. Why? Because it's a closed and bounded subset of R. Then by Hasibul theorem, it's a compact subset of R. And U1 bar, the closed arc, being a subset of the Hausdorff space R2 is also Hausdorff. So it's a fact that follows from the point set topology. Recall it from point set topology. If you don't have it on the top of your head, just follow the following argument. Okay, so we want to show that if um, if one has a subset of a Hausdorff topological space, then the subset equipped with the subspace topology is also Hausdorff. Okay, so how to see this? Um, uh, let A be a subspace of a Hausdorff space X. Okay, let X and Y be 2 points in A. Okay, so since X and Y are points in A, they are also points in X. Why? Because A is a subset of X. Okay, since X is Hausdorff, you can find two disjoint open sets in X containing X and Y. Okay, so which means that there are disjoint open sets U and V, so that X is contained in U and Y is contained in V, and the intersection of U and V is the empty set. Okay, now since X, well, since X is in U and also X is in A, we have X belonging to A intersected with U. Okay, also since Y is in V and Y is also in A, one has Y belonging to A intersected with V. Okay, now what is A intersected with U? Intersection A intersected with V, the other set, is equal to, by elementary set theorem, it's going to be A intersected with U intersected with V, and since this is null set, the intersection is going to be empty as well. So we have shown that for two points in A, to distinguish points in A, there are two open sets, A intersected with U and A intersected with V, containing those 2 points respectively, such that their intersection is the empty set. It means that the subspace that we have, the subspace A, or the subset A equipped with subspace topology, is also Hausdorff. Okay, so this way we see that the closure of U1, meaning that the closed arc U1 in the unit circle S1 is also Hausdorff, since S1 is Hausdorff. Or you can think of it as U1 bar being a subset of the Hausdorff topological space R2 is also Hausdorff. Okay, good. So let me erase it. So this map So this is a continuous bijection from this compact set to this Hausdorff space. Okay, so this is continuous. We have shown that it is continuous. We also have shown that it is a bijection, and we have shown that U1 bar is Hausdorff, so it's a continuous bijection from a compact space to a Hausdorff space. Okay, now recall corollary to proposition 5 from our point set topology review notes. Topology review notes. Okay, so it appears at page 19 of the LaTeX note. Okay, so that tells us that a continuous bijection from a compact space to a Hausdorff space is a homeomorphism. Let me write it for you here. A continuous bijection from a compact space to a Hausdorff space is a homeomorphism, which proves that this map P restricted to the closure of Vn, this map is a homeomorphism. Now, since restriction of a homeomorphism is again a homeomorphism, one concludes that P restricted to Vn only, not the closure of Vn, just Vn. From Vn to U1 is a homeomorphism. Okay, and it's a homeomorphism for each n in the set of positive integers. Okay, so hence U1 is evenly covered by the map P. Okay, in the same way, one can prove that U2, U3 and U4 are also evenly covered by P. Okay, therefore P from R to S1 given by this formula Px equal to cosine 2 pi x sine 2 pi x is a covering map, and R is a covering space of this unit circle QED. Okay, good. So this was the detailed account of this covering map. So let me take a break here. We'll be back in the third segment with the definition of local homeomorphism. Thank you for attending this second segment.